Hi. Hi, warm regards. Welcome to the next session with Applied Mathy. And here we go. So today's video is about circular functions. Have you ever wondered what a circular function is? Mathematically speaking, a circular function is nothing but a trigonometric function, wherein the input which goes inside is an angle, preferably in radian, and the output which comes is a real number. I'm going to take up this in a little bit more detail and we take a closer look. Let me consider a unit circle. So I have a unit circle and there is a point P. Let me suppose that it has a coordinate A and a coordinate B. Now I know from all my coordinate geometry skills that my A is this part. Am I right? I'll go and change the color of my pen and I will say that this is the B part. If I ask you what is the cosine of this particular angle T and what is the sine of this particular angle T, can you think about it? Yeah, we know that cosine is based upon hypotenuse, so it comes out to be A. Why no hypotenuse? We know my hypotenuse is 1, right? And what is sine of t? Sine of t will be B. The idea is both the coordinates of P of x and P of y, they can be written down as trigonometric functions. And more beautifully speaking, they both lie on the circle. That is another reason why trigonometric functions are called as circular functions. Interesting, right? Let me check it. If you have got it just right, so there is a question, you see it on your screen. Am I right? Which of the following represents the hypotenuse of a right angle triangle? I'll give you a slight hint over here. If you've started thinking, you've marked the answer, very good. But I want you to think the triangle which is being formed on the circle, right? So what will be the hypotenuse? Well, that's a big hint. If you still want to think, you can pause the video because I am releasing the answer out, which is the radius. Absolutely correct answer if you thought so. All right, going forward, what is a radian? Well, historically speaking, what I would say is that angles have been measured since centuries or years or whatever. So the measure of the angle was right angles, 1 right angle, 3/4 right angles, and so on and so forth. Then came up the second unit of measurements of angles, which we said were degrees. So what they did, they divided one right angle into 90 equal parts. Post that came the sexagesimal system, where each and everything was divided into 100 such equal divisions. Now comes what we call as a radian, which is a circular kind of a measure. Well, interesting to note, right? If you have a circle of a radius r and there is an arc length which is also equal to the radius r, whatever angle they subtend at the center is 1 radian. Imagine, now please imagine what all angles would be greater than 1 radians, what all angles would be less than 1 radians. And, every time we think about angles, we are always in our primitive unit of measurements. So here, I have a GeoGebra applet. So I can show it to you. I'll just switch on my screen and try to shift it to the GeoGebra applet. So what do I see here? Basically, if I move this point P, my arc length is depicted by this E value. You can see it here. I have a fixed radius, 2.32. If you want, I can change it, right? And I can now try to make my arc length equal to 3.02. See, and that is the angle I receive. So that is a particular degree measure which correspond to what I call as 1 radian. But what if I want to, just find out in terms of the other conversion, how do I do that? So for that, we'll come back to the slide and let us see how we can do that. we have one basic concept, the angle proportionality with the length of the arc. So I'm going to do a little bit quickly. I will say AOQ and I will take it as AOP. You can do it with me very fast. What is AOQ? Arc length I'm going to consider is AQ. And here, what is my arc length? It's going to be AP. Perfect. So AOQ, I know it's a quadrant of a circle. So I will say it is one right angle. AOP, I have already defined it as 1 radian. Well, that is the way they write 1 radian. You can skip C and just write down radian over there. That is perfectly fine. What is AQ? It is pi r by 2, assuming the same concept, circumference upon diameter is pi, absolutely, and AP is radius, right? Because that we said is equal to the radius. Perfect. So that defines my 1 radian equivalent to 2 upon pi into right angles. All right, so I have defined a particular value. I will say it is 2 upon pi times the right angle. So what is basically a right angle here, depending upon whichever unit that you like at that moment, and as we usually convert it into, degrees. So I would say 1 radian would be 180 degrees divided by the pi. Wow, that is the achievement. And we are ending the session with a question rather, or if you say it's a numerical, whatever you say based upon a concept. So I'll take you to the next slide, last slide for the day. Angles, if I ask you, find out the angle of a decagon and you have to give me the answer in radian. Well, if you're looking for the answer, I can give you the answer in degree. If you don't want to get the answer and you're still thinking times, you can pause the video. So when you do it, your answer would be 144 degrees. And then you're going to convert it to radians. And you are very, very smart children. If it is 144 degrees and I want you to convert it into radians, you will say pi by 180 degrees. Here, convert it, you would get it as 4 pi by 5, right? And the ones who want a little bit of help can just extend it. We know this angle is 36 degrees. How do we know? Sum of exterior angles, for any polygon, it comes out to be 360 degrees. So this would be 144 degrees, linear pair. Interesting, right? So we'll stop here. That's a mild introduction to our topic on trigonometry. All right. Thank you so much.